So please welcome René and Heinrich to their talk.
All right. Make us earn it. Okay, so last year I was talking on FOSDEM about how to create a social news stream for a social networking application. And shortly afterwards, I was visiting my good friend Heinrich in Oxford, and we discussed this problem of scientific communication. And the problem basically is, how do scientists find new relevant publications? And who here in the audience is actually a scientist to some degree? Who's writing papers, who's working in academia? Or who has any degree and experienced this? Okay. So the problem usually is that you're interested in a very specific topic, you know the keywords, some other people publish something under a different keyword, it just doesn't match, you don't find the publication unless you have been to the conference. A lot of the papers you get are really recommendations from friends, and we talk to many people from different fields and they all experience the same problem. They might use Google Alerts, they might use news feeds, but they say 90% of the stuff is just not useful, and sometimes they even figure this out after reading this. And the other problem that scientists approach is, how do you connect with people that are interested in the same topic? I mean, of course you can go to a conference, but not everyone is accepted to the conference, and sometimes you just don't meet the people. And again, you want to talk to those experts. So these are the two problems that we experience, and what we think is there's a solution to this, and this is the academic graph. So the academic graph mainly consists of two things. One thing is the social graph that really exists, where I can talk to Heinrich about a topic. And the other one is the citation graph, because once I cite someone, there's a lot of knowledge inside this citation. The problem is, if you look at the web, so the problem is the social graph is hard to get, because you need to be Facebook or you need to be LinkedIn, and you need to have all that stuff. If you look at the web, or if you think of the problem, you think, well, the citation graph might be easier to get. And we can assure you it's not. The citation graph is just not available due to the open access problem. And that's why we included this one slide about open access that we think on an open source event is a really good idea to talk about this. Right now, this is how society works. The taxpayer pays people like Heinrich and me, scientists, to do science and research. Afterwards, we are still being paid by the taxpayer to do the peer reviewing of the entire process. Then my university pays a fee that I can go to the conference and pays all that stuff. And last but not least, the publisher has the paper, puts it behind a paywall, and the library of my university again pays money that other people can read my publication. And this, of course, is really not cool, and we think we need to change this in a little way. And so that we have more open access on this entire thing. And last year at WWW conference, I met Tim Berners-Lee, and he really said something like, think of how you want the world to be, just imagine that. And then go geek and do it. Just go and program this. And we did a little review of websites that are in the field of academic publications, and we put out 3 dimensions. We have open source on one side, we have open data, and we have user-generated content. And what you can see is, besides the last row, which is what we're planning to do, nothing exists. Either the people are not open source, so no one can really contribute and make this stuff better, or people just don't give out the papers. And what we also think is important in a platform like this is that people can actually really go out and discuss some stuff. And some of them have user-generated content, but not everyone, so it's really a problem. So maybe you want to add some more stuff to this, and then go on with the first benchmark that we did.
Yeah, I think it's really essential to have access to the citation data, because I mean, all of these players, I mean, there are many excluded which are in the fields of scientific publishing, don't have actually access to this graph of papers. And so these are the players who basically have this information, and there's Google Scholar and Microsoft Academic who did a lot of PDF mining and generated this graph, but they don't give it out for us to have it and do stuff with it. So we are forced to use their recommenders and their views on the data, and we can't actually exploit this to build our recommenders, which might be better or more suitable to the kind of thing we are in. So yeah, this is the one thing, and yeah, CiteSurf, for example, is another open PDF mining platform, but it gives out their data, but somehow the quality is a bit problematic. And it doesn't allow people to connect on the website. So there's still room and the need actually for people building this open citation graph and making this data available.
Sorry, I forgot the vision.
Yeah. So please talk about it.
Okay, sorry, I just forgot that there was still one more slide before Heinrich really contributes to his part of the talk. So we have a proposal on the web that you can read on blog.relatedwork.net/proposal, where we talk to a lot of scientists. And what we really want to do, and what we also want to introduce you in the talk already with the very first demo, is that we want to create this social network for scientists, and it basically should consist of a Q&A system. So we see in StackOverflow, and also especially in Math-Overflow, that a lot of fruitful discussions can be going on in a Q&A system. We want to have open access to all the data, so in the best case we already get some publications there. We really want to make use of the open citation network, because in this way we can really make stronger recommendations, because we know exactly the interests of everyone. But we want to also have linked open data and discussions of the discussions and the metadata that we generate. So not only the PDFs, but also the content that we have on our website, we want to provide this. So I'm thinking of Peter and your talk, where you said you need data sets. One thing that Heinrich already did is using the archive, which is a free preprint repository of 250 gigabytes of scientific publications, and he extracted the citation graph of this. Yes, it's on our website. And it's a Neo4j format, actually, so you can just download the Neo4j database. I really don't know.
It's our new exchange format. We always give out our data as zip Neo4j databases, and our plan is to establish a standard.
No. So anyway. So we want to do the strong recommendations. We want to really work on the alt metrics movement, so create more trust with these kinds of metrics and don't rely on the peer reviewing, and have the personalized news feeds. So now I think it's really time to go to the data structures for QA system and our first benchmark.
Yes. So we talked about, first thing, scientific publications and networks of that. Second thing, discussions. So we started out with the citation data, and we used a graph database for that. What could be better than Neo4j to store all these papers and all these graphical structures or relations between them? And so we wanted to have also discussions within our system. So one thing we ask is, can we build a discussion system on top of Neo4j, on top of a graph database? And the answer is, of course, yes, very easily. You have a thread, and you have a lot of posts hanging at that thread, and they're just naturally organized in terms of nodes and relationships between them. And you have author relations between the posts and the users, so that might be like the same user authoring several posts, but it really fits neatly in a graph database. Also note that this traversal is really efficient. So once you are at the thread node, it just takes you 2 steps, to search to get all the nodes, and you do not really have a lot of overhead hopping along nodes you don't need. So it's a pretty efficient model for discussions, which scales very well if your discussion system gets very large. Because the thread size, the local size of the graph is still small, you have only so many posts in a thread, but the data set can get really, really large. So, and then we thought, okay, this is nice, but maybe we can make a benchmark. And we can see, does it really perform well? So we compared it with other models for discussion systems. So this is the traditional one you have. For example, StackOverflow or WordPress does use this kind of relational model. You have a table of posts which are linked to users and threads, and use indices to make this look up fast. But these are joins, so if the database gets really, really large, the join gets slow, because you have to logarithmically go through the posts table and make the lookup with the index. So in theory, it doesn't scale that well. And the third model, document stores, are really popular. So you can have documents, and there's a thread, and of course you want to deserialize a lot of, denormalize a lot of data if you use a document store. So one possible model would be to have one document representing a thread, having all the sub-posts in there, and have some users which author the posts, and you can have extra documents for that. Also here the lookup time is pretty efficient, because document stores are usually hash table lookups, which are also constants in the size. So we did some evaluation of that, really hands-on, and we used open data for that. So our friends from Stack Exchange actually have published their data sets, and we just took 5 of them, real-life discussion systems. The first one, Unix discussions, it's really, really small. The biggest one is the super user data set. We couldn't fit the largest data set, the StackOverflow data set, in main memory and generate our benchmark, so I dropped this one and went with this. And here's the actual results from the benchmark. So we have 3 databases: Neo4j, the relational model, Mongo, the document store model, and MySQL, the traditional one. And you see MySQL is still the fastest. It's all is pretty fast. It's just 2.3 milliseconds, so it doesn't really make a huge difference. You see Mongo is going up slightly. I don't really know why, but it's going up a bit. And Neo4j, it gets faster actually if the data set gets larger. And we don't really have an explanation for this. I think it's the data sets are all pretty small still. It's just 500,000 nodes. We don't really see the scaling. And there's a lot of like side effects still in the data which generate a lot of noise. So the upshot maybe here is doesn't really matter. Everything works as long as your discussion system isn't crazy big and you are not really stupid with your data model. Okay, so now is the time for a little Q&A in the middle. So I just wanted to ask, who of you is a Python fan? Yeah, I see a few hands. I consider myself a big Python fan. And the next question is, who likes Neo4j?
And Python. And Python.
And Python. So I love both. But of course I wanted to do the benchmark with Python. And what happened? So here, the first 2 bars are the Python benchmark for Neo4j. It's really bad. Mongo and MySQL, it's also Python. So these are also Python. So that's really, we thought, what?
Which Python?
Both.
We did both. Yeah, we did the native one. There you have this JPipe library, which is not too performant, and then we did the REST API too, and it's also not really performant. Partly due to the fact that it can't do keep alives on the TCP connection. It's somewhere I found it said the header, but it actually, if you look at the via, it always sent 3 packets, a whole handshake for every lookup, and that isn't performant. It just doesn't work. So please give us a fast API for Python.
Wait for about 2 months.
Oh,
Thank you very much.
I would love that. Okay, perfect.
Okay, so I want to talk a little bit more about our data model and our requirements, because this was the discussion benchmark, the Q&A part. But as I said, we also have a social network here. So what does our social network look like? Basically, we have papers and authors, and the authors write the papers. But we want to put several different queries and out from this bipartite graph that we get. So I just want to introduce some of them here with some graphics, and then I have a list of them, but what I basically want to show you is all of them are the same. So for example, what I could ask for is, what are the co-authors? And if I want to do co-author graph, basically it's a graph traversal, and it's breadth first search level 2. I mean, I start at one paper, at one author, I go to the paper, go to the other authors. In Neo4j you can do backward traversal, so it doesn't matter in which direction the relationship goes. So here I can do a breadth first search 2, and I get co-author relationship, which gives me a lot of valuable information about my authors. But we're also interested in citations. As I said, Heinrich extracted all the citations from arXiv, which is already 1 million papers, I think, something like that. And we already see which papers cite which papers. But in real life, I want to know to which other researcher do I pay a lot of attention. So how would you answer this question? Well, assume that I'm sitting here and I write some paper. I could see who do I cite, who wrote this, and I get this relationship here, which is again is a graph traversal with depth 3. So it's again breadth first search. And the last question that I could also ask about is what authors are similar, because I want to do recommendations on this. I want to say, well, if you're interested in this author, you're also interested in these other authors. So how does this look like? Well, the author has some paper, and the paper cites some other papers, and this happens again with another author. And now I can do, again, a search over the papers that are cited by us both. So when we two cite the same papers, I assume we're similar. I could do this model differently. I could already say, if other people cite my papers in common, so if we both write papers and other people cite us, but of course going in this way gives us much more information, because maybe I'm a new scientist, I just wrote one paper, and I already can measure a similarity score with many other authors.
And that's something that's really, really similar, really, really important for the recommender, because this is the one. If you are this author, you want to write an email to this author saying, "Hi, how are you? What are you thinking about this topic?" So this is really the good recommender you get out of this graph.
So as I said, Heinrich did this on the archive. The archive is basically almost a full data set of last 10 years of mathematics, more or less. And he has a PhD in math. He studied in Oxford. And we're using these recommenders on Heinrich. And he's like, dude, I never heard about this one guy. I mean, most of them in the list, of course, he knew very well. I mean, he has a PhD, right? But there was this one guy who's like, he's doing exactly the same stuff. I have to look into his work. So it's really useful doing these kinds of things because the scientific community just has those rare chances of talking to each other. So what are the other kind of queries that we want to know? We want to know, well, what are the papers written by an author? Which papers cite another paper? Which papers are cited by a paper? It's all just like one link. The other ones is what are frequent co-authors of an author? Which authors does author X like to cite in the other direction? Similar papers, similar authors. So I just introduced them, but you see they're all just breadth first search. Okay, did you see any tables? We didn't, so we decided graph database is good in this kind of scenario. Graph database works reasonably well in the discussion system, so let's go for graph database. And well, we had some lessons learned because we already have a database of like 8 gigabytes and it's growing. What can you learn from doing this? Well, the first one is let's have a look at Cypher. So Cypher is the query language of Neo4j, and while I was working with this, I was thinking of, well, should I use the core Java API, should I use the Traverser framework, or should I use Cypher? And I asked just simple friend of a friend queries, so co-authorship, right? And when I did this on my archive dataset, which again is a 1 million node graph, already pretty big, I saw that with the core Java API, I could fire something like 2,000 queries per second. So 2,000 times in a second I can handle the requests of what are my co-authors. If I do this in Cypher, it's getting maybe 100. So Cypher is really slow for these kinds of traversals. So if you want to go and have really high performance in Neo4j, I suggest to go to the core Java API, even though the code maybe gets a little bit longer. As you see, Neo4j 17, 18, 19, and Cypher is getting even slower with the newer version, whereas the core is getting faster in the newer versions. And we also did this with data sets of different size. So when we made more and more queries, we already see that there's really an order of magnitude between Cypher and the core API. Yes, it is.
Yeah, it's like we have not gone into query optimization.
Yeah, and I know that the query language is just being defined, but the message is here when you want to be fast. Yeah. Go for the other part. Another lesson that we learned is even though 1 million traversals, which are basically joins, seems a lot, you have to look out. Because with 1 million traversal steps, I can, as I just saw from the benchmark, ask 2,200 requests per second for a co-authorship relationship. But as I said, similar authors is a breadth first search of depth 4, and those things grow exponentially, so there's only like 5 requests left per second. So what do we do on these kinds of graphs? I mean, we do this as the data mining bulk process, where we can already do it for various authors at the same time, because one traversal can already collect this for a lot of pairs. And then we really create the new edge in the graph. So not for all pairs of co-authors or for all similar authors, but for the most of them. And in this time back, we're again at something like 4,000 requests per second that we can handle.
In-graph indexes.
Yeah, something like this, yes. So we really separate between the raw data that we get and additional edges that we create by data mining. Another thing that we want to do, and we also talk about this a little bit after we showed the demo, is we want to do efficient search on the graph and do auto-completions and everything. So we calculate PageRank on the graph. And right now we do this in an iterative way, which really works fine. The only problem is we stored the PageRank value in a property. So every time in the iteration when we update a node, which happens every step, I mean every time, I mean this is what PageRank calculation is about, we actually need to make this persistent, and that doesn't work at all. So our solution right now, as long as we have the memory, is we create this use hash map of nodes and floats where we can like write on the memory all the time, and at the very end when we did all our PageRank iterations, we can just flush this out to the disk, trying to group as many transactions as possible, and then we're also fast again. And the PageRank calculation on the 1 million nodes archive graph was something like maybe 6 or 7 hours, so it's reasonably fine. Yeah? Oh, 10 minutes. Okay, perfect. So these are the 4 lessons that we learned. Just don't use Python with Neo4j, at least up till now. Hope anyone here is going to fix this. Another lesson that we... Thanks. No, we have to do with this one, sorry. Another lesson that we learned is use Neo4j's core API, so fixing Python might even not work, because Cypher also is not so fast right now. When we have expensive traversals that are really going far, maybe you just want to cache the results and store them already in the graph. And writing properties, at least in the PageRank calculation and these kinds of things, also is not that fast. So try to avoid this. Okay, what we then did is we decided on which technologies should we use for the design of the entire application. So we went to GWTP. Whoever used here GWT, Grid, and GWTP? Okay, quite some people. So for the rest, I'm just pointing out what the good sides about this are. So if you use Grid, we have a clear separation of server and client-side code, which is really nice. Ajax really helps you to only transfer the data.
You should say what Grid actually is.
Yeah, Google Web Toolkit. So it's a framework from Google that you write your server code in Java. And the funny thing is you write the client code also in Java, but Grid compiles it to JavaScript, and then it's as an Ajax application deployed on your browser. Because the server is in Java, we can use all these technologies like Neo4j, Lucene, Tomcat. It smoothly integrates. And on the client side, we also have powerful APIs for web programming because it's made for this, including HTML5. When you Google a little bit about using Grid, you very fast come to GWTP, which is a Google Web Toolkit platform. It's a model view presenter framework. It does injection handling for you. It already comes with history support, which is always quite a mess in the Ajax application. It does code split if your JavaScripts are getting too big. It really helps you on testing, although we haven't implemented this, and we promise we will do at some point in time. Okay, so I would say it's demo time.
Okay, let's see what we have.
Okay, already pointing out at this point in time, we need designers. We're not designers. We really have a focus on usability, so we think our recommenders do good usability, but it doesn't look fine yet. It's not online. I mean, it's right now on our notebook computer.
So right now we see my my personal page. I've written 2 papers, which is something. And we see here already some useful things which are in the graph. It's there's up to 2 papers which I wrote, and René talked about the different metrics we have for authors. For example, similar authors. These are authors who are cited by or cite similar papers than I do. And this is a friend of mine. He worked with me in Bonn. This is my PhD father, and he's an Italian guy I know very well also. So this is just basically my friends. Yeah. Here are my co-authors, which is currently none because I have not written any paper with somebody else. Maybe René will be here soon. And here, these are the people that I cite a lot, and no, this is the people who cite me a lot, and this is the people. No, it's all the way around. So this one I cite, this one I'm cited by. Okay, so
the interesting thing here is, just to point this out, there was no HTTP request involved so far. This application is really fast because once I request this site, the local graph of Heinrich is just transferred to the client side, and the rest is just JavaScript and working, which really helps a lot.
No HTTP requests. Okay, now let's go maybe to a paper site. So there we are. This takes 12 milliseconds here. And I see the references. Some of them are matched, others are not. So there are some strings still here which I couldn't match to other publications from the archive.
Which ones are about K3 surfaces?
So now we have a find box which René implemented. So
none of them?
None of them. Oh, it's there. There it is. So I have an instant filter here. There's also no HTTP requests, and it filters all this whole big list with every keystroke that I make.
5 minutes.
5 minutes left.
Okay, great. So what do you want to know now?
I think you should also show the auto-completion at the top.
Okay, so I will type a letter, and we see auto-completion here. So this is an autocompletion which is in two parts, the blue one and the black one. The black one is the usual autocompletion, which is on all authors and on all titles I have in the whole database. The blue one is actually a personalized autocompletion, which is implemented by René. He can say a few words about that, which is localized on my personal network. So here's only authors that I cite and only people that I know. So this is really convenient and gives actually a really, really fast way to browse this graph. So I can just explore the graph by just working with this autocompletion. And as I'm just clicking around a bit, I mean, I don't really have to follow what I'm clicking. I don't really know. But you see how responsive this is. These are all database queries, and not all of them are lying in the cache. Well, this obviously isn't.
Well, the physicists are always power users.
Yeah, but there are some really, really big nodes with a few thousand papers, and there are a few thousand traversals which are done for the rendering of the page. So we are quite happy with the performance of Neo4j here.
Yes. Okay. So let me just use the rest of the time for the personalized autocompletion, maybe. So when you want to do personalized autocompletion, and I think I already created a blog post on this maybe a year ago, something, it's really embarrassing because I did all the personalization on the server side. So what happened is if the user was logged in, I did some expensive query on the database, seeing what is all of his interest, building really something in the memory, a search index in the memory of the server attached to the ID of the user. And then every time the user does a request, really looking at this context and merging this with every other stuff. What you can do in GWTP very efficiently is do it on the client. So we use Lucene as a search technology, which is also nice because it's very well integrated in Neo4j. And for the autocompletion, everyone would say, well, you use Apache Solr. But we didn't do this. We used just this really plain, basic suggest-tree script written by Nikolai Diethelm. If anyone knows him, say thank you. I don't know who this guy is. There's this one script on SourceForge, nothing else. And it really is performant. Whenever you want to do autocompletion, this is the script and data structure to go. We use this. And the funny thing is, since it's plain Java, I can just also put it on the client side. GWTP compiles it, and I can just use the same code on the client side with just one more click. So what the personalized autocompletion does is I take the PageRank values that are already calculated for every node, and then if I see Heinrich, I just say, well, I do breadth first search level 2. I collect everything that I see, collect the PageRank values, transfer this to the client once, maybe 50 kilobytes. Then the client puts it in the search index, and then everything is just there. I think we have one more slide to go. Yeah. And this is basically, we put the slides online, and here you can just see some links to our GitHub repositories where we, on one side, have the application, which is related to work.net, but also the open citation corpus. We separated the entire data collecting. So right now there's archive inside, but we're already working on PubMed Central and some other data sources.
Yes, we should mention here another name, which is David Schotten, who worked on this open citation corpus, and actually a company called Cottage Labs, whose Richard Jones is also here, is currently helping us out with the data import.
That's true.
Yeah.
Then there's our blog, and there are some articles about the benchmarks and stuff that we used. So we ask if you have questions, otherwise we had some questions, and thanks for your attention.
It's very, very fast, 1 minute.
All right.
First, have you ever tried Postgres with recursive SQL support?
No.
Because this would be also very interesting, because you are at the moment just measuring the limitations of a normal relational model. And second, perhaps you could include Git or GitHub or GitLab, whatever repository.
Yes.
And another kind of paper, because also people contributing to repositories.
Okay. Just
looking at starring
things. Just to answer this in the whole thing. There's this blog post that we talked about, and on this we have the entire roadmap and vision where we want to go. And we want to have a lot of user-generated content that is cleaning up and providing meta information. So what's the Twitter handle of some scientist? Where are some source code repositories and these kinds of things? So we want to include all this stuff. And for your Postgres thing, the benchmarks are online. So you are free to at least go with those benchmarks and use the same datasets and hack it in. And maybe this is also good for the benchmark that you say, well, they should be open source, then people can extend to them.
What a good choice.
Yes.
So thank you very much.
You're welcome.